My first postdoc in 1970 was with Françoise Anglais and Robert Brout, and they had written a paper on Higgs, and Peter had written a paper on Higgs a few years earlier. And at that time, nobody was paying any attention to them. And the reason was, at that time, it was not known whether non-abelian gauge theories were even renormalizable until that was shown later by 't Hooft and Veltman. But I remember Robert pointing to this paper that they wrote in 1964, and he kept on saying to me, "This is a very important paper." And he was quite annoyed that nobody else seemed to think so at the time, but gradually, of course, everybody did. The other connection that I have with the Higgs mechanism is the paper that Peter wrote tried to do everything with this famous double well potential, where you start off with an elementary scalar field. Now, I had been working in dynamical symmetry breaking, where you replace the scalar field by the expectation value of psi bar psi, and I'm a particle theorist. And it was working on dynamical symmetry breaking that led me into gravity, which is what I'm going to talk about today. So indirectly, I got into gravity because of the Higgs mechanism. So it's really very nice to be here today. I should warn you, I'm not on the regular team. I'm not in the dark matter camp, I'm not in the dark energy camp, I'm not in the string theory camp. I have a very different view of how gravity should work because of how I came into the subject. But the ground rules are, for a workshop, I have to give the party line. So I will tell you what all my colleagues believe to be true. And at the end, on the Friday, I'll talk a little bit about why I think dark matter and dark energy are really indicators that we have to go somewhere else. And I think I'm giving a colloquium on Friday at the end of this, my 5 talks, which will, my talks will lead directly into that colloquium on the Friday. Okay, so the references, I've written many papers. There's some review papers here, but the key reference is really Weinberg's book on gravitation that was written in the 1970s. And most of what I know in gravity I've learned originally from that book. And if you want to learn anything at all about gravity, that's the one that I recommend, because it's not about geometry, it's about gravity. And you have to use geometry, and we'll see during the course of these lectures why you have to do that. But really, it's about gravity itself. There's one other thing. Yes. Now, this is the outline that I think I sent everybody the notes. I'll try to cover all of these topics, but I'm going to work through from Newton and original gravity theory down to special relativity. When I get to curvilinear coordinates and tensor calculus, most people who approach gravity find that to be the most complicated, even though it's really what you're doing all the time, except it's a slightly more general approach. But you'll see that, because that's the key to working through the gravity theory. So I'm going to try to cover all of these topics. And what I'll be doing is I'll be lecturing on the board, but I'll keep the screens on the screen up above when I get to the material that you already have that's in the notes, so that you can cross-reference both at once. But I'm going to start, and the thing I did not include in the original notes that I sent you, is I want to go back even further and begin with the Greeks. Now, the Greeks really laid out the program which we call modern physics. Even though they had nothing to do with modern physics, they raised a set of problems. The solution to those problems leads to the work of Newton, which is the opening to the modern physics that we have today. Now, the Greeks introduced something called geometry. This is geometry. And it means geo is earth, meter is measure. They wanted to measure the earth. And they wanted to try to figure out the size of the solar system, the size of the earth, the size of the solar system. And I'll describe to you in a few moments how they did this. But at the same time, as discussing what we now would call cosmology, namely the structure of the universe in which they lived, they also dealt with another problem. So there was the shape of the solar system, but the other problem was the problem of motion. And the whole issue of motion is really the thing that will drive us to get towards the theory of gravity. Everything was driven by Aristotle, who said something that is rather obvious. If the force is zero, the velocity is zero. If I place an object on the table, until I move it by applying the force, it doesn't move. We now know that this is wrong. We now know that the velocity is constant, and that's Newton's first law of motion, and we'll see that everything that follows in physics follows from that first law of motion. In other words, try to understand what Aristotle got wrong. Now, how did the Greeks figure things out? Well, there are certain objects in the sky called the planets. Planets simply mean objects that move around with respect to the distant stars. And so the distant stars seem to be fixed in space, and the planets moved around. And there were 7 of them. And let me show you how we know that today. If I write down the names of the days, Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, and Saturday. No surprises. Now let me write them down in French. Dimanche. I'm sorry, I don't know what they are in Gaelic. Lundi, mardi, mercredi, jeudi, vendredi, and Sunday. Now we see a little pattern here. Let me just go to one of these colored ones. The Sun, the Moon, Mars, Mercury, Venus, Saturn. Jeudi was really Jupiter, who was the king of the gods. So what you see is the names of the 7 planets. Let's look at it. You might say, well, Tuesday isn't Mars, but Tuesday is Tyre, and Tyre was the Norse god of war. Wednesday is Woden, who was the Norse equivalent of Mercury, and Thursday is Thor. So in fact, the language that we use here in Britain is a mixture of Norse and Latin. And so the names of the days, and there were 7 of them because there were 7 objects in the sky that were seen to move around. We now know there are other planets, but none of those are discoverable from just by looking with your eye. You need a telescope. So in the pre-telescope era, there were these 7 planets. The 7 planets went in very strange orbits. If you take here's the Earth, and let's say that's Mars, then at one time in the year, Mars would be ahead of the Earth, and then a bit later on, the Earth would be behind Mars. And so this was, the pattern of Mars was a very complicated one, and this was called retrograde. It had a retrograde motion. And that they knew. And they tried to explain this retrograde motion. The Greeks believed in beauty, and for them the only beautiful possible orbits were circles. Circles, we'll see in a moment, is the only solution you do not get to Newton's laws of motion, to Newton's laws of gravity, except under a very, very special case, because it leaves out the centrifugal barrier. But we'll see that in a moment. So they tried to develop a system for predicting where the planets were going to be. And this was done by a person called Ptolemy. And this was done around 100 of the Common Era. So that's about 1900 years ago. And when we look at that model today, we look at it, well, it's wheels within wheels, it's cycles and epicycles, and we always laugh at it and say, this is pure nonsense, you're just trying to fit the picture. However, it was not until Brahe in around 1550, Tycho Brahe discovered that there was a conjunction that was supposed to occur between Jupiter and Saturn according to the Ptolemaic calendar, which did not occur. It was 1 month off. And so by that point, the errors in Ptolemy had accumulated in 1500 years to something observable. So then we knew that the theory was wrong. But if you now look back and you ask, has any other theory in the history of physics taken 1500 years before it ran into trouble? And the answer is no. Now, of course, we've only been doing physics for a certain amount of time, but the fact is, no other theory has lasted that long. And I don't want to be critical of my colleagues, but many of the things that we do don't even last until the next archive publication. Never mind 1500 years. So that was one of the issues. The other issue that Aristotle raised was, and this is the whole question, is it the sun that's at the center, or is it the earth that's at the center of the solar system? So is it the sun, or is it the earth? That was the question. And Aristotle came up with 3 reasons for why the earth had to be at the center. And they're very good reasons, and they all turned out to be wrong. One is, if it moves, we would feel it. Now, I don't want you to look at that and say that's so strange. We are going round the sun right now at 30 kilometers per second. You have absolutely no idea that that's the case. The sun is going around the Milky Way at 200 kilometers per second. Not per hour, per second. And you have no idea that that's the case. And the Milky Way is moving through the cosmos at around 300 or so kilometers per second. So these are absolutely gigantic numbers, and we have absolutely no sense that that's the case. The second argument he gave was moon would get lost. If the Earth moved, then the moon wouldn't keep going around it. So somehow the moon did not get lost. The third reason that he gave, which is actually a very good one, and he says no parallax. Now parallax means if here's the sun and it's the Earth that's moving around the sun, then some distant object would be looked at a different angle at different times of the annual cycle. And then its position in the sky would change. And he said, look, we look and we see we don't see that. Therefore, he presumed that it wasn't the Earth going around the sun. It was the sun going around the Earth. That was his argument. Now, the Greeks did a lot more. They discovered that the Earth was round. This is 1500 years before people thought the Earth was flat. They already discovered. They didn't just discover it was round, they measured the radius. And the way they measured the radius was the Earth goes around the sun. And they didn't know this, but they still got the right effect. The Earth goes around the sun, and let's see if we can do it this way. And there's a tilt. There's a 23.5 degree tilt, which means it goes around the orbit at an angle, which means that there's one day in the year where the sun is directly overhead when you're 23.5 degrees down from the North Pole. And that's called the summer solstice. And what they discovered was, because the Greeks were very close to that line, the Tropic of Cancer, I think it's called, and they discovered that there was a well right on the tropic in a town called Aswan, which is in Egypt, where one day a year the sunlight hit the bottom of the well. Every other day the angle's a little bit different, so it's slightly off. But then they had another well, and they discovered that there the sunlight did not hit the bottom of the well. And they measured the angular difference. They also measured this distance, so they knew theta and they knew s, and from that they could get the radius of the Earth. But s is our radius of the Earth. And they got a number which is pretty close to the number that we have today. So they actually were able to measure the radius of the Earth. Now, how did they know that the Earth was not flat? Well, there's a certain phenomenon which is very important, which is the Earth. Let's say there's the sun, there's the Earth, and there's the moon. When the Earth gets between the sun and the moon, there's a so-called lunar eclipse. And in a lunar eclipse, if it's a partial eclipse, you can see the shape of the Earth on the face of the moon. And it was a disk. They couldn't say it was a sphere because they only had a one-dimensional picture. But they could see that it was not a plane. They could see that it was a disk. And so they knew that the Earth was round. People know this but didn't quite register with them, because if you stand on the coast, you can look around you, you can see it's almost a circle of ocean. It certainly is not a plane. And you can see ships coming over the horizon. So where do they come from? And you can see them go back over the horizon, and lo and behold, the next day they come back. So obviously there was some kind of a curve. It turns out that in the time of Galileo, the telescope was invented, and the Venetians wanted this device because when a ship came over the horizon and started approaching them, they wanted to know if it was friendly or not friendly. And the telescope gave them the advantage that enabled them to become a dominant maritime power. It also gave Galileo the ability to resolve all of the difficulties that the Greeks had had. Now, the other thing that they did was they didn't just see the general shape. From a knowledge of eclipses, they actually figured out the size of the solar system. It was quite remarkable. And the reason is the following. Between when the moon enters this region here, when the moon enters that region, until it leaves, they could time how long it took to go across, and from that you could uniquely determine exactly where the moon was. And if you want me to do that, I'll go through that in the tutorial, how the Greeks actually figured this out. So they were able to determine there's a unique point where you have to go through, and from that you get the radius of the moon, the distance to the moon. Now, the other thing that is quite remarkable is that in the solar eclipse, there's the Earth, and we just had one a couple of weeks ago. I don't know how visible it was in Scotland. It was a very big thing in the United States. Totality went right across the United States. It was really quite remarkable. In totality, the moon just fills the sun. Not smaller, not larger. That means that they both have the same angular diameter. So the same angle. And that angle is about 1/4 of a degree. The Greeks were able to measure that. Now, from that piece of information, they were then able to discover not how far the sun was away from us, but that it was further than the moon. Because the moon blocked it completely. And they were able to get the ratio of the diameter of the sun to the distance to the sun. Now, how did they get the distance to the sun? they noticed one more thing. If I put the sun here, and there's the Earth, and there's the moon, then there's one point at which the moon is exactly at 90 degrees. And that's when you have a quarter moon. It's not a full moon. The full moon, of course, is, the new moon is here, the full moon is over there. That's the quarter moon. And what they noticed was that the time it took to go between those two, let's call that T1, and the time it took to go from those two, T2, were not the same. And therefore, T1 over T1 plus T2 would give you that angle. They were able to determine that angle directly by knowing this ratio. And from that angle, now they could get the size of the sun and the distance to the sun. Now, we look at it today, and they did this more than 2,000 years ago. They had no telescopes, they didn't know calculus, they had to scribble on a piece of papyrus, but they worked the whole thing out. At the same time, on the geometry side, we got the whole work of Euclid. Everything that we'll do in general relativity is to find out where Euclid can generalize. How you can go beyond Euclid. I'll give you the answer straight away. Euclidean geometry has x1 squared plus x2 squared plus x3 squared plus x4 squared is equal to a constant. Or constant squared. You can think of that as a Euclidean geometry system. The only difference was, you put a minus sign there, and that's non-Euclidean. And that is the doorway to general relativity, because it's also the doorway to special relativity. And so it was understanding where Euclid could be changed that leads us into the modern theory of relativity. Okay, so the Greeks discovered this, the size of the solar system, but the most important thing that they discovered was that far and away the largest object in the system was the sun, not the Earth. Therefore, you would naturally think the sun would be at the center. Now, let me just clarify one thing. If we ask the question, is the sun at the center or is the Earth at the center, that is absolutely a meaningless question, because you can just change the coordinate system. The question is not the sun and the Earth, but you take some other planet. You need a third object. And with that third object, then you can define a center. Namely, does the third object, how does it behave when you work in the sun system? Now, you know this in a different way. I think you've all done this at some time. You're on a train, and you're sitting at a station, and there's a train on the other platform, which is also stationary, and all of a sudden you get a sense that you're moving. And you don't know, am I moving to the right, or is that other train going to the left? So what do? You look to the platform on your side. That's the third reference point. So it's only when you have that reference point that you can determine which one of the two trains is moving, because the relative velocity is not meaningful. Okay, and that's the same story. Okay, so the Greeks had this picture. They certainly had shown that the sun was at the center. It was the heaviest. I mean, not the heaviest. It was far away the largest object. Now, I must tell you this. There's one thing I've never figured out. How the ancients explained the day, because the day is a 24-hour cycle, not a whole annual cycle. And we understand it's the Earth rotating around its axis, but the Earth's supposed to be stationary. Therefore, I don't know exactly how the Greeks could have done that, but the one thing I could guess is that they had the sun only shine for half the day. And it was sort of like one side was shining and it goes around, and then the other side would be dark. Though, of course, then you have the question, well, wouldn't it be dark all over the Earth at the same time? But they didn't have the communications mechanism to determine that. So I actually don't know. Maybe you can puzzle over that. Maybe somebody will come up with an answer. How could the Greeks have explained the 24-hour cycle in a model in which the Earth didn't move? So that's sort of an interesting question. Anyway, that's the heritage. And we see two kinds of questions. One is, the nature of the universe, and the other is the problem of motion. Now, this remained in place. Aristotle had the status of an authority figure that was not challenged for something like 1,500 years. And that's how powerful he was. And then people started to look at this again, and I think you all know, Copernicus was the person that realized if you had the sun at the center, and let's see, draw this. If you had the sun at the center, and then let's say there's Mercury, there's Venus, there's the Earth, and then there's Mars, and they're going round the sun, then they can overtake each other on a circular track. So an observer on the Earth would sometimes see someone in front and sometimes see someone behind. And that explains the retrograde motion. So the retrograde motion is understandable in a heliocentric system. Very, very, very simple. Now, you realize from that why astronomy and gravity are so difficult. We're in the wrong place. We are in this planet that's moving. It's like being on a carousel. If you, let's say you go to an amusement park, you stand at the side, you can see the carousel going round and you can easily describe it. Now get on the carousel and try to describe the amusement park. It's much, much harder because you're in the wrong place. So we unfortunately are in the wrong place, and we've had to adapt physics to handle all of those things. So the first person that proposed this was Copernicus. The notion that we are not in a special place, that we're the third planet along, is not a particularly important place, is called the Copernican principle. Now, in modern cosmology, the generalization of that is called the cosmological principle. And I will discuss that when we start discussing cosmology. Okay. So Brahe played a very unusual role. Physics has to be very indebted to Mr. Brahe because he was a nobleman. Now that doesn't sound like it's anything significant, but he was a very, very powerful person. He came from a very powerful family, and he had access to the King of Denmark. And he went to the King of Denmark and he asked the king, I said, look, I want to build an observatory. And the king said, how much is it going to be? He said, well, it's about 1/10 of the budget of Denmark. That's what we call big physics. And because he was so powerful, he was able to get the king to sign on to it. And with that center, he was able to monitor the motions of the objects in the sky from night after night, and to take very, very careful measurements, very accurate measurements. And from that, a picture emerged which was clearly in contradiction with Ptolemy, which was Copernican, but Brahe was very, very conservative. He didn't want to write down a theory where the sun was at the center. So he basically took the Copernican system and made a translation of the coordinates to put the Earth at the origin of the coordinate system. So it's essentially Copernican, but he didn't concede to that. He had an assistant called Kepler, and he gave Kepler the challenge. He said, figure out the orbit of Mars. So Kepler tried to improve on Ptolemy, tried to work out the orbit of Mars, and nothing worked. And the reason that nothing worked was because he was going round in a circle, but that's not enough. You also have to go round with uniform velocity. You don't change the velocity as you go around the path. he realized that that wouldn't work. He knew that something had to give. What he gave up was equal velocity. And that becomes the rule, equal areas in equal times. But when you sweep out a path in equal times, the areas are the same. So how do you make the areas, if that area is bigger, how do you make it smaller? You reduce the velocity. You have to change the velocity according to the area. And we'll see how that works in a moment. But then he discovered that that didn't work. And so he realized he was going to have to not just give up uniform velocity, he's also going to have to give up circles. And now he's faced with one of the most difficult problems that any human being has ever been faced with. And that was this. If the orbit of Mars was not a circle, then neither was the orbit of the Earth. Therefore, he had to figure out what would the orbit of what does the orbit of the Mars look like to an observer on the Earth in this unknown orbit of the Earth? And he does that before the invention of calculus, before the invention of any kind of analytic technique. It's even before the invention of the telescope. Yes? Have to give the...
Maybe not. Did they have Cartesian coordinates?
I'm sorry, did they have what?
Did they have the Cartesian coordinate system?
Descartes is about the same time. No, but they didn't really think. I don't think they did that. But I'll explain what Kepler had to do. Was he had to calculate everything with the sun at the origin of the coordinate system, and then it becomes possible. And what he discovered was the orbit was an ellipse. Now, we are incredibly lucky, and the reason that we're incredibly lucky is that the orbit of Mars is almost a circle. It has a very small eccentricity, which enabled him to find it. If the orbit had been elongated, it would have been much, much harder to find. So, two pieces of luck. One is that we just happen to be at this odd place in the solar system where the moon blocks the sun exactly, has the same angular diameter, only for us. It doesn't have the same angular diameter for anybody else. And it just so happens that the orbit of Mars was very close to a circle. But he realized that it was an ellipse. So Kepler resolves the problem, and the answer is ellipses. Now, it sounds simple, but it's very puzzling, because an ellipse has two foci, not one. So what's at the other one? There's only one sun. So there's one sun here, and there's nothing at the other focus. So how could that be? If there were two suns, that would make much more sense. And the reason is because the other planets also have one focus at the sun, but the other focus is somewhere else. There's only one common focus to the motions of all of the planets. And that's why that one common focus becomes the important point. Okay. So he resolves the issue of the ellipse, and he comes up with the third law, which is that the radius, I think it's the radius cubed divided by the square of the time for the orbit, is the same for all of the planets. And it's a very good rule, and what that number is equal to, in a moment we'll discover, gives us the mass of the sun. Okay, so that was Kepler with his three rules. Then Galileo, who also addresses the problem of motion, we'll come back to what he does with that in a moment. Well, you all know the story of the two objects falling at the same rate from the top of the Tower of Pisa, which probably never happened, but nonetheless it's the apocryphal one. I mean, only because of air resistance. So he had the telescope, and he discovered certain things. One of which was that the planet Jupiter had a set of moons. And they would be seen going round Jupiter, and they would go out of sight when they went behind Jupiter, and then they come back. And he saw 4 of them, and I'll tell you their names. Io, Ganymede, Europa, and Callisto were the 4 Galilean moons of Jupiter. Now, what was so important about this discovery was they weren't going around the Earth. They were going around Jupiter. And not only that, somehow Jupiter did not lose its moons. So he doesn't know why Jupiter does not lose his moons, but he does know that Aristotle got it wrong. That cannot be the right answer. Also with Tycho Brahe, with his measurements, you could measure parallax. And one of the interesting things was that there was a supernova occurred in 1572. There was a supernova. And a supernova is a star that explodes, and while it explodes, it suddenly becomes incredibly bright. And we'll see later on that that's the key to understanding the accelerating universe, that gravity isn't always attractive. And what he discovered was he could measure the parallax of this supernova. And he was able to show that it was not within a solar system. And of course, it would always be believed that any object that moved must have been nearby. But the idea that you could have something that whose behavior would change in time as opposed to change in space was something new. So Brahe obtained that. Galileo sees the moons of Jupiter, and he knows that something. So now we know that everything is wrong with Aristotle. He also sees the phases of Venus. Venus has phases just like the moon has phases. It's just that they're not as clear to us without a telescope, which meant that Venus must have been in orbit around the sun as well. And as its angle changed, the amount of it that's illuminated that then reflects back to us, that could be exactly the same thing for Venus as it would be for the Earth. So he sees that Venus has phases. He saw that the sun had sunspots, that the surface of the sun was not complete. I mean, if circles are good, then spheres are good, and pure spheres are very, very good. And the sun was not a pure sphere. Now, by the way, when we say that an object is spherical, that's not what we mean. If I give you a football, the surface is spherical. But that does not mean that as you go inside, that the density is uniform. And in fact, any of you who've ever blown up a football will know the density is not uniform. So, spherical density does not follow from the spherical surface. And that because the surface is two-dimensional, the density is three-dimensional. So the two are not related, but we always use them interchangeably. When we say something spherical, we only mean it looks spherical, not that necessarily that the density is uniform. And what we know, by the way, is, we'll see in a moment, Newton was able to measure the mass of the Earth. We already knew the radius of the Earth, therefore we get the density of the Earth. But the density of the Earth is much higher than when we are on the surface, which means that the Earth has a core. So, you're pushing these ideas, you can come up with a remarkable discovery that the Earth must have a core. It's spherical symmetry, which means the density depends on the radius, but it's not uniform in the radius. So, we now know that. Okay, so those were some of the things that Galileo found. He was trying very hard to come up with a proof that the Earth was moving. I mean, it was pretty clear to him that the Earth was the Sun was at the center of the solar system, and that caused him a lot of grief with the Vatican. But nonetheless, he was trying to prove that the Earth was in motion, and he tried to explain the tides by the pull of the moon, which we know is correct. He didn't get it quite right, but the idea was good. Because you have this huge amount of water that suddenly washes up onto the shore. or it rises. I mean, when the tide rises, the amount of force that's required to do that, you just calculate it, it's just phenomenal. And he was able to realize that something had to provide that force. And he realized it was the moon, but he didn't quite get hold of it. So everything was set. Galileo had shown that the other rule of Aristotle, that you need a force to get a velocity, he'd also shown that that was wrong. And he realized that you could get uniform velocity without needing a force. And we refer to Galilean invariance as an invariance that leaves the velocity constant. So if you have x prime is x plus ut, then v is equal to v plus u. And then it's v dot is equal to v dot. Then it's the acceleration that's constant and not the velocity. So those are all the pieces, and it was Newton who puts them all together. So how do I do this? I think you might have to log in.
Okay.
Yeah. Okay, so finally, Newton's the person that puts all of these things together. And let's see what he does. So, Newton's three laws. One, F equals 0 implies velocity is constant, means that to change the velocity, you need a force. So force not 0 implies dv dt not equal to 0. What's the relationship? Force is mass times acceleration. So, why is this so extraordinary? If we just think about a person in even Aristotle's time, riding in a chariot. You're sitting in a chariot, you don't feel anything unless you hit a bump. Then you suddenly feel you get jolted. So what you feel is the change in the velocity, not the velocity. And that was a somewhat obvious thing once Newton tells it. I mean, look, in physics, everything goes always the same way. The moment that you realize something, it is dead simple. Even if it took you 20 years to find. After you see, once you've got the principle, then the whole thing's obvious, except finding it is the hard part. Which is what you're all tasked to do if you're grad students. You're doing research. That's your job. Is to find things that nobody found before. And you can look at people like myself and Danan, who were once graduate students, is to tell you that it's possible. That human knowledge has not yet reached its peak. So you need a force to get an acceleration. Newton basically was saying, if you have ice in a hockey game and you hit a puck, it will go on forever. It doesn't happen because friction slows it down. And the one thing that was holding people up since Aristotle was that we live in an environment where there's always friction. And therefore we never see the effect of how does a universe look if there's no friction. But if there's no friction, then uniform motion is automatic. Because it's friction that slows things down. There's something else I've puzzled over with Aristotle, and that is, if I throw a ball, which the Greeks would do, I provide the original force to start the ball moving, but it keeps going, even though I'm not continuing to push. An object on the table will only keep moving if I push it. If I throw it, there's no friction. There's air resistance, but let's assume that's negligible. There's no friction, so it keeps going. So I don't know how the Greeks were able to explain why something should keep going once it had started. And of course it's Newton that resolves that. The third law is sort of action and reaction are equal and opposite. That's if I push against the wall pushes me in the opposite direction. And if you watch the swimmers in the Olympic Games, that's when they reach the end of the pool, they push hard on the wall to send them back in the opposite direction. So that's the third law. So these were the three laws of Newton. The third law turns out to be very, very simple. It's conservation of momentum. So it's actually a lot more general. And it's also not true. Because when two objects collide and then they go back, they bang against each other and bounce back, you use conservation of momentum. You have the homework problem that you always get as an undergraduate is you've got a pool table, you send a ball, it hits another ball, and the ball goes off at an angle, and you have to calculate the angle. But that presupposes that those are the only participants in the process. When two objects collide with each other, they also emit gravitation, a gravitational wave. And momentum is conserved, but only when you include the momentum of the gravitational wave as well. Except, it's so weak that you don't measure it. But it's true, momentum is conserved. In the modern language, this is the statement that the covariant derivative of the energy momentum tensor is 0, which we'll meet shortly. But what is going on here is the statement that you've also got to include the momentum of any object that might be emitted at the same time. It doesn't just apply to elastic processes. Okay. Now, the second law is a law which is very, very strange. Because if you have motion in a circle, and you have uniform motion, then you don't change the velocity. Well, not quite. You don't change the magnitude of the velocity. But you do change the direction. And if we look that one, and then that one, then I can write this one minus that one. Probably doing it wrong. Yeah. This one minus that one, and there's the resultant. The acceleration, the force, is towards the center. It's the change in the velocity, but you change the direction of the velocity. So the change in the velocity is the initial velocity, the final velocity minus the initial velocity, and that doesn't point in the direction of either of them. It points towards the center of the circle. In fact, if we have a ball on a string, then you're tugging on the ball along the string, and yet it's going in a circle. Feynman tells a nice story. He says, the ancients used to think that the angels were pushing the planets around in their orbit. He says, they almost got it right, but they were pushing in the wrong direction. And so we have this really interesting thing that the direction of the change in the force is not the same as the direction in the force. And that's actually the key to understanding motion in more than one dimension. So that's one of Newton's big discoveries. Now if we do the same thing then what you discover is that the object goes around and the velocity is on the tangent, so it's constantly changing its direction. But the restoring force is always towards the center. And therefore, I took it off the board, the Earth doesn't lose its moon. And why does it fall in a circle, or close to a circle? It's because as it's falling, it's at the same time moving around, and they compensate for each other. And that's why it remains in a circular orbit. So Newton solved the other problem that Aristotle mentioned, namely, why don't you lose the moon? Though the better question is, why doesn't the moon lose its Earth? Why doesn't the moon shoot off? And the answer is because there's a restoring force which is always pulling it back towards the center. Now Newton goes on, and of course, what I did say before, if I write the velocity is v initial plus a constant, let's say v0, then the force doesn't change. So you can take a velocity, you can add onto it a constant velocity and not change the force, because the time derivative of the constant velocity is 0. So Newton realized that the first law is consistent with the second law. This, as I've said at the beginning, the first law is not just the first law of physics in the sense that it's chronological. It's foundational. It really is the piece from which the whole of general relativity eventually will follow. Okay. So Newton comes up with his laws, and we write down Newton's law of gravity. This is Newton's law of motion. And this applies to any kind of motion. It has nothing to do with gravity in particular. It's presumed to hold for everything. He comes up with his law, and the force is equal to m times mg over r squared, and it's in the direction towards, it's an attractive force towards the center. Now, if we have that force, then it will give a mass times an acceleration. And what Newton realized was that those two masses, the one that appears in Newton's F equals ma, which we now call the gravitational mass, is not necessarily the same, the one we call the inertial mass, is not necessarily the mass that appears in Newton's second law of motion, in Newton's law of gravity. And the reason why is because I could have had capital M be the object that's being pulled, because I can look at F12 or F21. So it's always the case that this has to be gravitational and that one has to be gravitational, because either of them could be the one going around the other one. So he gets this law. He realizes that the two masses may not be equal, but as best he could tell within the measurements that they had, was that mi was equal to m. Now it turns out that later on, Eötvös proved that this was indeed the case, and then Einstein said, well, there has to be a reason. There must be some reason for why those two objects come out equal. And that reason is called the equivalence principle. And the equivalence principle, if you apply it to gravity as well, will lead us to general relativity. Okay. So that's that's Newton's discovery. If I just now take an orbit, then the orbit is always going to be in a plane. It's a two-dimensional plane. One second. And that's because the angular momentum, which is conserved, if I give you a plane, there's only one direction that's defined by that plane, and that's the perpendicular to the plane. Because any line in the plane is not unique. Yes, there was a question. Yes, sir.
Yeah, is there a nice story as to how Newton got over 1/r², or was it just a pure guess based
Oh, well, it was already known for light. Namely, the intensity of light would fall off as the inverse square. In fact, that was one of the motivations for the inverse square. Was simply that if you have a light source and then you have an object over there, how dim is it? And the answer is it goes like 1 over the square of the distance. Yes, sir.
Doesn't the fact that you can have like inertial and a gravitational mass only become apparent once you have other forces that don't include mass? Like presumably they didn't know like about electric attraction or anything like that.
Well, the answer is you've jumped the gun. You see, the question is, where does mass come from in the first place? Mass is coming from all of the dynamics. I mean, that's what I do. That's what I said at the beginning. I work on dynamical models of mass, where all of the mass of an object comes from its own interaction, whatever the forces are. And what this is sort of saying is, well, if the inertial masses, like exchanging Higgs bosons, for instance, holds an object together, and it's equal to the gravitational mass, then maybe gravitational interactions could also hold an object together. And the question is, can we make sense of that? And the answer is yes. I mean, that's still an ongoing research problem. But yes, this doesn't ask the question of where does the mass come from. But modern physics absolutely does. It's the origin of mass is the whole driver of our modern theories of physics. The Higgs mechanism gives some of the mass, but there's more. I think that's what you're asking. And that more usually goes under the fancy name of gluons and quantum chromodynamics. But those are very...
It's more like, sorry,
Yes?
how do you even realize, like, if you don't have a force that doesn't include mass in it, right? Because they don't only know gravitation. Like, isn't it just a feature of your theory that mass cancels out, right? Like, how do you even realize that they could be different?
Okay, you see, I have to jump ahead. If I write down a wave equation, I put a mass in it. That mass is called the inertial mass. It's whatever fields are in that wave equation. If I then calculate the geodesic in that field, I will find that, okay, I didn't want to do this, yes, but you see, d2 x lambda d tau squared plus gamma lambda mu nu dx mu d tau dx mu d tau equals 0 is the geodesic equation. And the whole point of this series is to explain this. But the only thing I can do here is I can only put one m. And it has to be the same m for the inertial piece as for the gravitational piece. Not because to enforce this relationship. It's simply, if I were to put any constant here other than 1, that linear combination would not be a general coordinate vector. And that's the thing. In the end, it's the geodesic equation is telling you that this is not a vector, that's not a vector, but the sum of them is. But with a unique weighting. So what I call the equivalence principle is the statement that these two have the same weight. If you do that, you multiply by m, and you want to associate this with gravity, then you can't avoid inertial mass equals gravitational mass. But it has nothing to do with what was the dynamics that made the m in the first place. Okay, but that's a nice question. Okay, so let's go on with Newton, and let's just write v squared over r is mg over r squared, and therefore v squared goes like mg over r. And that means that if I plot the velocity against the distance, the velocity is going like the square root of mg over r. Next one. One more. There we go. And that is what Kepler would give us. That's the Kepler law. That the velocity goes like the 1 over the square root of the radius. And if you plot the planets of the solar system, around, and you put their velocities around the sun, you can see that you get the sequence. The higher the velocity, the closer it must be. And that's exactly what we've got. Mercury, then Venus, Earth, Mars, Jupiter, and Saturn were the ones that were known. Now, if you look at the Earth, the orbital velocity is 30 kilometers per second. Now, you can check that. We know the rate, we know the distance from the Earth to the Sun, about 90 million miles. We know it takes 1 year to go around. Calculate the velocity. You do that as an exercise. You'll be astonished how big it is. I mean, it's 30 kilometers a second. That's a huge velocity, and we have no sense of it at all. So that's the so Newton explains the ellipses. Now what happens is, and this is why are there ellipses? If the force is an inverse square, then the force is always directed towards the center. And so if the force is directed towards the center, why isn't the orbit a circle? You swing a ball on a string, it goes around in a circle. Why isn't the orbit in a circle? Well, the answer is, it's a three-dimensional problem. You have centrifugal energy, namely Li plus 1 over mr squared. It's called the centrifugal barrier. That's the amount of energy that you get by being in motion. You're just I omega squared in moment of inertia times the square of the frequency. So if you now plot the total velocity, namely LL plus 1 over m r squared minus mg over r, it looks like that. That's how it looks. Now, we solve the centrifugal barrier, as this is called, solves an enormous problem. If I just have a 1 over r potential, then everything collapses to 0. There won't be stable orbits. You just go straight to the origin, because that potential is unbounded from below. There's always a state of lower energy. So how do you prevent all the planets from collapsing into the sun? The answer is, you have them in orbits with an angular momentum. The angular momentum is conserved because, as I said a moment ago, if I have a surface, the only direction that it uniquely defines is the normal to the surface, and that doesn't change as you move around the surface. And so conservation of angular momentum is guaranteeing you that there is a centrifugal barrier. And therefore the orbits are those. And what you see immediately is that the bound state orbit has a point of closest approach and a point of furthest distance. So that motion is therefore an ellipse. And that is the discovery. So why can you have an ellipse with a central potential? The answer is because you need a centrifugal barrier to prevent collapse to the origin. And that works in such a way that the balance is always such that the bound states are have different point of closest approach, which I think is called perigee, and furthest distance is called apogee, and they have the two of them. There's one unique point where the two come together, and that would be the circle. So the ellipse is the general solution. And if you work through Newton's law of motion, you can show that the orbit is of the form 1 over r is a plus b cos theta, where in polar coordinates, where this is r and that is theta, and a and b are constants which depend on the size of the two sides of the major and the minor axes of the two the ellipse. If you want me to show that, it's a standard result in textbooks. I'll do that in the tutorial if you want me to go over that. Okay. Now, from v squared over r is mg over r squared. We also get v squared is 2 pi r times t squared over r, and therefore you get r t squared is equal to mg over r squared, and therefore you get Kepler's law, r cubed t squared is constant. So from Newton's discovery of the central potential, he gets the motion of the orbits to be in the ellipses. That's Kepler's first law. He gets that equal areas in equal times. That's just conservation of angular momentum. That's the second law. And the third law, namely that the radius cubed is universally proportional to the square of the time of the orbit, is the third law. And they all fall out. Absolutely amazing. However, what is more amazing is that all of the planets, the whole lot, are determined by one number, the mass of the sun. So how many, I've got all of the different planets. We have a universal law. It's universal in three ways. It has a universal strength, g Newton. It has a universal mass, the mass of the sun. And it's an inverse square law. It's universal in three separate ways. And this is the Newtonian gold standard. That's why we think that this theory is correct. Is because so many phenomena can be explained from one simple rule with a universal mass. It's not one mass for Jupiter and a different mass for Saturn. It's the same mass for all of them. Yes, sir?
So we've got this idea that the radius has to stay within this potential barrier. You have the sort of the aphelion and the perihelion, and you have to stay between, and you get the ellipse. So, I mean, if you conserve angular momentum and you conserve energy and whatever, what's to stop the orbit just going from going in a random funny path?
I'm going to come to that. That's because it's inverse square.
Okay.
If it was inverse cube, it would you'd be right. We'll come back to that in a moment. Okay. So that's the layout. It was a very good question was just identified. There's one very special feature of a 1 over r squared force. And that is that when you go around in an ellipse, you come back to the same place that you were the time before. And that's called no precession. The orbit does not precess. Now, in principle, you're absolutely correct. If there's a centrifugal barrier, you could have gone anywhere, as long as you stay between the two extremes. And in fact, technically, the actual orbit of the planets is this. They actually do spiral in, but that's because of the emission of gravitational radiation. But that's an incredibly small effect. But they actually are not perfect ellipses. But the reason why this is so special is because there's a second principle for the inverse square law, and that's this. We preserve the line perpendicular to the plane, but the major axis of the ellipse is also preserved. It's also time independent. And that vector that goes along the major axis is called the Runge lens vector. And the Runge lens vector actually means that you have a higher symmetry for the inverse square law than simply rotational invariance. Heisenberg and Pauli solved the spectrum of the hydrogen atom before Schrödinger using matrix mechanics, not wave mechanics. And they were able to do this because they had that second symmetry, because that second symmetry is a property of any 1 over r potential, and the Coulomb potential was also 1 over r. And so you don't get any precession of the orbit. If you were to change the potential, then you would miss the second time round, and you would keep on missing, and it could accumulate. And what we know from the study of Mercury is very nice. Being closest to the sun it has the largest number of orbits. It takes 3 orbits in one of our years. So in 100 years, it's taken 300 orbits. Now Mercury is a very easy planet to observe because it's so close to the Sun. And over 300 years, it was discovered that there was a precession. A very small one, 1 part in a billion. It's a very small effect, but there was a precession. And so there was a problem with the solar system. There was a second problem, which is the earlier one. And that is that the planet Saturn was not quite on the curve. So there were 2 problems that the ancients had known, or at least 19th century physicists had known, that Mercury was slightly off the curve, and Saturn was slightly off the curve. It was recognized that there should be near to Saturn some other object that was pulling on it. And Uranus was discovered. And it comes in exactly the right place. This is perhaps the most spectacular achievement of Newton's law of gravity. Is the requirement that a planet exists that no one had seen before, because you need a better telescope. Herschel had the telescope to do it. And they found Uranus. Uranus itself was also slightly off the curve. And then it was proposed that Neptune exists. And Neptune comes in. And then something funny happens. Neptune wasn't quite on the curve. And so it was proposed that there was yet another planet that was pulling on Neptune, which we call Pluto. Only 2 things happened. Neptune, since it's been discovered, has yet to make 1 whole orbit of the solar system. It takes about 200 years. We haven't done it that long. So the data weren't as good. And as the data were refined, it was gradually realized that there was no problem with Neptune in the first place. The only thing was, and in the meantime, Pluto had been discovered. So what could you do? The only thing you could say wasn't a planet. The only solution was to pretend it wasn't a planet. So Pluto comes in just too light to have, too small in mass to have affected the problem in any serious way. So the solar system, we see, constantly reaffirms the Newtonian principle. You do have the curve, you have these little perturbations due to planets tugging on other planets. But nonetheless, the main rule that it's all driven by the mass of the Sun is it is holding up. Now what about in the interior? Mercury, on the other hand, was also a problem. And unlike the outer planets, there could not be a problem with there couldn't be another planet pulling on Mercury that hadn't been seen before. One was actually guessed. They invented a planet called Vulcan. Vulcan was never discovered. And so they realized, and this is the question I was asked a moment ago, that it must be the case that if Mercury's off the curve, there must be some modification to Newton's law, to the inverse square law. So people tried 1 over r squared to the 1 plus epsilon, and they looked at that. But what happened was, and this was the great achievement of Einstein, was that when Einstein developed special relativity, general relativity, the first thing that he did was he found a modification to the inverse square law, which precisely accounted for the precession of Mercury. And that was nearly 100 years ago, it was 100 years ago, and that's remained true until today. Now, to understand what's going on is d squared is mg over r, and v squared over c squared is mg over c squared r. mg over c squared will meet in general relativity. That's called the Schwarzschild radius. That's the putative radius of a black hole. We'll see how that happens. But that's the v squared over c squared correction is a term of order 1 over r. Therefore, there's a v squared over c squared correction to this law, which will give me something that goes like 1 over r cubed. The v squared over c squared correction. And that's exactly the right number. So what Einstein eventually does is he asks the following question. we've seen that things are very nice for constant velocity, but observers aren't required to move with uniform velocity. Observers can accelerate. So then he asked the question, how does Newton's law of gravity look like in an accelerating coordinate system? And the answer is the Einstein equations. And that gives you the v squared over c squared correction, which precisely explains the motion of Mercury. Now, of course, it also does this dramatic thing. It also modifies the geometry in such a way that even light has to bend as it passes by the sun. And it was the bending of light by the sun, another v squared over c squared type effect, which cemented in people's minds the realization that this strange notion of space-time that Einstein has was the way that nature works. Now, so what we find is that we're going to get a v squared over c squared correction to everything. And those v squared over c squared corrections are going to be very, very important. And so we've met the solar system, and that's the I think maybe you sit here. Okay. So that no, not yet. There we go. So we've met the solar system, and there's tremendous amount of information in that solar system. Now, when we go to galaxies, which we'll get to later on, you do exactly the same thing for galaxies, and it doesn't work. It's disastrous. So you invent something that makes it work. It's called dark matter. So dark matter is the way to make the same story hold for galaxies as holds for the solar system. The only problem is you don't have the universality. Every galaxy has its own dark matter halo with its own mass. There's no universality in the way that we do galaxies compared to the way that we've done the solar system. Now, the other concern of Newton, of Newton's law, was raised by Mach. And one second. Yes, sir. Oh, there was a question? No. Okay. So Mach said the following. Suppose you have x double dot equals 0. And now you write x prime is x plus a half g t squared. Then x prime double dot is g. So, you have an equation with gravity and an equation without gravity. You can change the right-hand side of Newton's law. Well, it's not forbidden because this is a transformation that says that v prime is v plus gt, which is not constant velocity. So it doesn't obey Newton's first law or Newton's second law, but observers, you're allowed to do it. There's nothing wrong with it. And what they discovered was that Newton's second law of motion was not preserved under certain kinds of transformation. To explain what it is, if I were to write x prime is x plus u0t, then x prime dot is x dot plus u0, if u is a constant. That's called a linear transformation. X and t are treated as equal with the coefficients being independent of x and t, whereas this one is nonlinear. That's a nonlinear transformation. And Newton's laws of motion don't have to be preserved by nonlinear transformations because Newton's first law is only holding for linear. But more than that, this transformation that you make all the time, x is r cos theta, y is r sine theta, is also nonlinear if you treat r and theta as the variables. It's also a nonlinear transformation. Why? Because circular motion requires force. So it has to be different. So we actually see, and this was Mach's concern, we actually see that there are a lot of problems in Oh. Does this go? How do I move the screen? Yeah. Oh, you got it. Oh, I was looking at that. Okay, thank you. So, Mach's problem is a remarkable thing. It was a driver for Einstein to develop general relativity, and in the end, it didn't satisfy Mach's principle, even though that was its motivation. What was Mach's principle? Mach said, well, how do we decide which coordinate system do we use? And so Mach suggested that there's some interaction between what's going on here and the rest of the universe. And that fixes the frames in which Newton's law of gravity holds, and those frames are called inertial. One of the worst things that you'll deal with if you teach introductory physics is if you use the term inertial frame. You'll basically chase everyone who's not a physicist away from physics. But the technical term is, Mach would say, the interaction between the local and the global fixes the frames in which Newton's law of gravity will hold without these nonlinear modifications. We now know that that is wrong. The geodesic equation doesn't care about the rest of the universe. It basically is saying is not that you need a law to fix the frame of Newton's law of gravity or Newton's law of motion. You need a frame, Newton's law of motion that will hold even when you're nonlinear. And that's this term here. This a half gt squared is that one. That's what it can. We'll see how that works. So the first discovery of Newton was Newton's set of motion laws. We saw that there's a problem with Mercury, which was resolved. I should also say the notion that something was pulling Saturn that you could not see, in the modern language, is dark matter. And then you discover it. So this is the first ever success of dark matter theory. You actually proposed the dark matter and you found the dark matter. Not being in the dark matter camp, I also say that so far it's the only success of dark matter. Because up till now, no one has ever found any dark matter in any accelerator experiment or researches underground. This room is full of dark matter, if dark matter is around. Well, that shouldn't bother you too much, because this room is full of cosmic microwave background radiation from the Big Bang, and it's also full of solar neutrinos. And we've taken generations to detect the solar neutrinos in the microwave background, so maybe, in your lifetimes at least, not necessarily in mine, maybe somebody will figure out how to detect the dark matter in this room, if it really exists. But nonetheless, that's the dark matter idea. So, after Newton, the next big discovery was special relativity, and special relativity is really driven by the Maxwell equations. And I've written down the Maxwell equations here. I think it was Maxwell himself that wrote them down here, not me. And there's some cheats involved in these equations, even though they're very familiar. Let's just take the first one. Gauss's law of electromagnetism. Give dot E is equal to whatever the source is, rho over epsilon 0. We learn that in infancy. Something goes wrong. When Gauss wrote this down, that was for a static charge and a static electric field. Charge at rest produces an electric field. What about a time-dependent electric field? Well, we would immediately expect a time derivative of the electric field to appear. But that's not Gauss's law. Gauss's law with time dependence did not change. even though the electric field is time dependent and the density is also time dependent. But that's not what Gauss wrote down. But nonetheless, that's what we call Gauss's law today. And it's really not what was written down. And it's a whole jump. Now, the other law that we have is, and this is the important one of Maxwell, del cross B is equal to mu0 times J. That's Ampere's law. But then Maxwell realized that the dE dt, mu0 epsilon 0, dE dt, that the time derivative of the electric field doesn't appear in Gauss's law, it appears in Ampere's law. That was the great insight, is what he called the displacement current has to be put into Ampere's law, and that's the law which gets modified, and that's the thing that leads on to everything we understand about electromagnetism. We call these the Maxwell equations, though that was the only piece that was due to Maxwell. Everything else was due to Faraday and to Gauss. Gauss's magnetism, div dot B equals 0, and the other one is del cross E plus dB dt. Yes, plus dB dt equals 0. Faraday's law and Gauss's law of magnetism were already known. What Maxwell did was he actually unifies them. Now, if we look at Maxwell's equations, we can see why they had to be unified in the way they were. How many equations do we have? Well, we always say there are 4, but it's not. There are 8 equations, because 2 of them are vector equations. So we have the div dot E and the del cross B, so that's 1 and that's 3, and they add up to 4. And then the other 2, is 1 and 3, they also add up to 4. So actually, Maxwell's equations can be written as 8 is 4 plus 4, and 4 have a source, namely the electric charge and the electric current, and 4 don't have a source. Except the whole issue of magnetic monopoles is whether or not they should. And that's not yet resolved, or at least still no sign of a magnetic monopole. Okay. So they actually break up into 4 plus 4. And 4, you know, is the number which is special to special relativity. Because we have 3 x's and t, so we write x, y, z, and t is also 4. And so the number 4 is the thing that underlies Maxwell's equations. And you don't think about that unless you recognize that the 2 vector equations are really, each one is three separate equations. Okay, now you can manipulate these equations, and of course that's what makes Maxwell one of the most well-known people in history, is you can try to, if you work in a vacuum, you can immediately show that that you get waves, electromagnetic waves, and the reason is, as the magnetic field starts to fall, the change in the magnetic field generates an electric field, and as the electric field starts to fall, it generates a new magnetic field. And so there's a sustaining action, and so you get wave propagation, which you would never have gotten without the Maxwell displacement. So the B makes the E, and the E makes the B, and it keeps on going. And then you discover that the waves travel with a velocity which is 1 over u0 epsilon 0. Is that right? Yes. And you put the numbers in, and I would imagine that when Maxwell did this, he probably didn't sleep for a week, because he discovered that the mu0 that you got from the magnetism and the epsilon 0 that you got from Gauss's law gave you a number which just happened to be the speed of light. It could have been anything. It has the dimensions of a velocity, but it could have been anything. But it wasn't. It was exactly the speed of light. And this was quite a staggering discovery. And we are forever indebted to Maxwell for having made this realization, because what he's really telling us is that electricity and magnetism and light are the same. They're all electromagnetic radiation. It therefore won't surprise you that if Einstein could recast gravity as a wave equation, there was going to be gravitational radiation. And we'll see, and not only will we see that, you will know that LIGO had actually detected gravitational radiation about now 10 years ago. Now, almost 100 years after Einstein said that it should exist. But there are some puzzles. There are some problems with Maxwell's equations. The first one is, well, you've shown that the velocity of light has that number, but in which coordinate system? If I'm moving with a velocity v, does the velocity of light become c prime is c plus v? What's supposed to happen? And if it does, then why doesn't the equation tell me? So the first thing is it does not specify the frame in which you want to measure this velocity. The second feature of it, which is puzzling, is this. If I have a particle at rest, and it produces a charged particle at rest, produces an electric field. That's Gauss's law of electromagnetism. If I have a charged particle in motion, then I get QV is equal to a current, and I get a magnetic field. That's Ampere's law. So let's just make a slight change. Let's leave the charge at rest and let the observer move in the opposite direction with the velocity v. What does the observer see? What can he see? Well, you said charge at rest only produces an electric field. So the observer's in motion. But motion produces a magnetic field. So what the observer actually sees as a force, Q, is E plus V cross B. That's why there has to be a Lorentz force. The Lorentz force is coming from motion. But what this also means is there's no independent definition of an electric field or a magnetic field. They are related. And one man's electric field is somebody else's magnetic field. They are tied together. And that means that the three electric fields and the three magnetic fields, altogether, there are 6 of them. Now 6 isn't 4. Now we always say 6 is 3 plus 3 because that's using three-dimensional language. What it is, 6 is 4 plus 4 antisymmetric. And 10 is 4 plus 4 symmetric. And so once you've got 4, you can take products and make symmetric representations. We have 10 components, which of course is going to be the metric of the gravitational field. And you have 6 components, which is F mu naught. So what we really have, the language here is, the universe is invariant under transformations that mix x, y, and z. That's the 3 rotations. But you could also mix x with t, y with t, and z with t, which are so-called boosts. So there are the 6 transformations. And that's why the number 6 appears. And so once we see the structure of F mu nu, of electromagnetism, we realize that we're going to have to use a very different language. But what were the problems? So the first problem is, which frame do we measure the velocity? Second is, if I move with uniform velocity past an electric charge, what do I see? That's a simple problem. And the answer is it has to be the same thing as if I'm at rest and the electric charge moves. It doesn't make any difference. You have to see it has to be the same. Now, third problem was, Newton says F equals ma. So increase F, you increase the acceleration, you increase the velocity. Therefore, you can eventually go faster than the speed of light. So if Newton's second law of motion is correct, then Maxwell's discovery that light waves travel at a special velocity, which we now call the speed limit, won't hold because you can go faster than light. And therefore there's nothing special about light. So something has to change. So poor Newton, when Einstein realizes that F equals ma has to change. And we'll see how in a moment. Okay. Now the other problem was the Maxwell equations have a certain invariance, which I've written up here. You write Ct prime is equal to x sinh theta plus Ct cos theta, and x prime is equal to Ct sinh theta plus x cos theta, and that preserves c squared t prime squared minus x prime squared is c squared t squared minus x squared. And that quantity is preserved, and if I look at the wave equation, I have here the one that you get from playing with the Maxwell equations, you get that that's an invariance. C squared t squared minus x squared minus y squared minus z squared is equal to c squared t prime squared minus x prime squared minus y prime squared minus z prime squared. Very nice, except it's not Galileo. Galileo only referred to the 3 velocity, not a 4 velocity. So the other problem of Maxwell's equations is that they don't obey Galilean invariance. So the laws of invariance of Newton and the laws of invariance of Maxwell are not compatible. Something has to give. We'll see what gives in a moment. And the last part, which was the important one, if you have a wave, waves carry energy and momentum. How's the energy and momentum transported? How does it carry the energy and momentum? Now what you know is, I speak to you, you hear me, because when I speak I excite the air molecules near my mouth. Each one knocks the next one and the next one and the next one, and then something starts vibrating in your ear, and a sound wave has traveled, a physical sound wave has traveled through the room. Now you also know that if you take a bell jar and you have a striker hitting a bell inside, you hear the sound and you see the strike. Now you take all the air out of the bell jar. You still see the striker, but you don't hear the striker. Therefore, the sight, the optics, the light travels in a vacuum. We see the light from the sun, it's 90 million miles away, where it's pretty much 1 hydrogen atom per cubic centimeter between us and the sun. So it's almost a vacuum. So light is traveling in a vacuum. Now Maxwell knew this, but he also knew that the only concept they had of propagating energy was a mechanical one, namely like sound waves. So he invents a mechanical medium called the ether. And so the last of Maxwell's concerns was you need to know how energy is transported, and so you invent an ether. Now this is something you can actually test. And it was done by Michelson and Morley in the late 19th century. And what it consists of is your sense of light from a source. It hits a mirror. One piece is reflected, it goes one way, another piece goes a separate way. The two mirrors then, it hits a beam splitter, and then the two mirrors reflect the waves back, and then they combine, and it's observed. So, Okay, so beam comes in, it splits, one piece goes there and comes back down, other piece goes there, comes back, and then they're recombined, and here's the detector. Therefore, you look for a fringe shift. Now, if there's an ether, it doesn't really matter which way the ether is going. Let's suppose it's going in that direction. Then the light picks up a velocity c plus u on the way in, and c minus u on the way back, but is always c when it goes perpendicular to the ether. And therefore you should see a fringe shift. And of course you all know they didn't see a fringe shift. Then they rotated the apparatus, just in case the ether was in some funny angle, and they never saw a fringe shift. They tried day and night, summer and winter, it didn't matter what they did, they never saw a fringe shift, and so they were able to say there's no ether. But they reached the wrong conclusion. The experiment was done in the horizontal. Suppose they had done the experiment in the vertical, which they were free to do. Then the light goes up and down, big deal, nothing happens. But in this line here bends and then bends again, because light undergoes gravitational bending. Therefore, if they had done the experiment in the vertical, they would have seen a fringe shift. And they would have said, we found the ether. And what they had found was the complete opposite of the ether. But the only reason, of course, they didn't, it's not that they couldn't do it, they couldn't do it. I mean, the effect is minimal. I mean, it's just not there. We now have done this experiment, by the way, which I'll talk to you later. It's called the Overhauser and Werner experiment, in which you send in a neutron beam, you split it like this, and you do see a fringe shift. It has been seen, and it is because of gravity. But for the moment, we have Michelson and Morley, which of course is a very famous experiment, leads us to the conclusion that there's no ether. Now, you all know that this was one of the driving features behind Einstein's work, though peculiarly in his paper on special relativity, he never said that. He never really discusses the Michelson-Morley experiment. He's sort of written as though he took it as obvious that they were going to not see anything. Because the whole discussion of all of the problems of Maxwell aren't resolved by finding the ether. I mean, by the way, you do solve what's the velocity of light? The answer is with respect to the ether. You do solve that problem. So some of it gets resolved, some of it doesn't. But what was not resolved was that the Maxwell equations and Newton's laws of motion had different symmetries. Ether or no ether. Now, it turns out that modern physics has restored the ether, but not in the mechanical sense. We now know you can create electron-positron pairs out of the vacuum. So the vacuum is not empty. It's a dynamical medium. But it's not a mechanical medium. Namely, the idea that we have particles bombarding each other to transmit a light signal, that's not the case. So the ether, in a sense, is not excluded. It has returned. But I will say that that's not what are called ether theories. Ether theories are really fixed frame general relativity, which is the complete denial of Einstein's entire program. But nonetheless, people do it because there may be some experimental possibility. Okay. Now, so let me just conclude, and I'll stop at this point after I've gone through this last description. Now, I want to describe to you what a very simple example of a nonlinear transformation is. I introduce polar coordinates, and so I can write down an invariant, which is x squared plus y squared plus z squared is equal to r squared, and the differential, sorry, I should have not written it down. I should have written dx squared plus dy squared plus dz squared is dr squared plus r squared d theta squared plus r squared sine squared theta d phi squared. If you write x is r sine theta cos phi, y is r sine theta sine phi, and z is r cos theta, then you preserve x squared plus y squared plus z squared is indeed r squared, but at the same time dx squared plus dy squared plus dz squared is dr squared plus r squared sine squared theta plus dr squared sine squared theta d phi squared. Now, we're going to introduce a really strange notation. I'm going to call, let's call this the length squared, the L squared. I'm going to write it as eta mu nu dx mu, where when a symbol is repeated, once as a lower index and once as an upper index, that's it's summed over. So that means sum on mu and nu, where mu and nu in this particular case is 1, 2, or 3. Now you can call x, y, z the coordinates, or you could call r theta phi the coordinates. So if I take x, y, z, then eta mu nu is equal to 1, 0, 0, 0, 1, 0, 0, 0, 1. But in the other case, with the polar coordinates, eta mu nu is equal to 1, 0, 0, 0, r squared, 0, 0, 0, r squared, sine squared theta. So the metric gives you a set of numbers which depend on the coordinates. Now what have we done? You just write dx squared plus dy squared is the line element, that's just Pythagoras. Dx squared plus dy squared plus dz squared is Pythagoras again, somebody asked me earlier, in Cartesian coordinates. What's Pythagoras in polar coordinates? The answer is this one. You can use polar coordinates to determine the area of a triangle, not the simplest way to do it, or the most sensible, or you can use Cartesian. But Cartesian, there's nothing special about Cartesian, they're just convenient. So we introduce a metric, and the metric is a way of doing bookkeeping. But now we've got a problem, and the real problem is this. We'd like to have 4 vectors. We'd like to have x mu would be ct, x1, x2, x3. We have to have 4. Remember, Maxwell's equations are based on the number 4. But we've only got 3 velocities. We don't have a 4th velocity. The velocity is just vx, vy, vz. So we have to make the 3 velocity become a 4 velocity. And so what we do is we introduce a dx mu ds, where ds is the invariant dc squared dt squared minus dx1 squared minus dx2 squared minus dx3 squared. And dx mu ds is now has 4 components, but what it is c dt ds, dx ds, dx1 ds, dx2 ds, dx3 ds. So that's got 4 components, but now we calculate eta mu nu dx mu ds, dx nu ds, and eta mu nu is, now I have to be a little bit careful. I'm going to have to put in a minus sign, and you'll see why in a moment. I'm going to put in a minus sign, so this becomes minus c squared dt squared over ds squared plus a 1, so that's dx1 squared ds squared plus dx2 squared ds squared plus dx3 squared ds squared, and that's an invariant. So this is equal to, actually it's actually equal to 1. It's a constant, because ds squared is that quantity. So what we finish up with is we can introduce a 4 vector, but it obeys a constraint. It only has 3 independent components. So what we've been able to do is we've been able to write the line element. I see what happened. We've been able. Okay. No, one more. So we're able to introduce a 4 velocity with a constraint. So now let's see what happens to Newton's law of motion. So we introduce a 4 vector force, but we've only got a 3 force. We only have a 3 force in the x, y, and z directions. But we can make a 4 force by introducing a quantity g mu. And let me write this out. And then g mu is equal to a 4 force, which is f dot v over c squared, 4 minus v squared over c squared to the half, and then f over c squared, 1 minus v squared over c squared to the half. And therefore Newton's law of motion becomes m d2 x mu ds squared equals u. And so we modify Newton's law of motion to make it into a 4 vector, even though Newton only wrote it down as a 3 vector. And we can do this even though we've only got three velocity components and three force components. But we can still make it into a 4-dimensional equation. Not only that, this quantity here, c squared dt squared minus dx squared, c squared dt squared minus dx squared, which is the invariant, the line element, we can also write that as dt, c squared dt squared, 1 minus dx over dt, d squared over c squared to the half. And that's where the famous 1 minus v squared over c squared comes from. The proper length is not the time, but it's the it's the dilated time. And that's the time dilation. So you have to write everything in terms of the time dilation, and then you can write Newton's law of motion in a covariant form. And now you can see, how can I get the force to be infinite and have to make the velocity equal to c? I have to make the velocity equal to c in order for the force to be infinite, which means I have to travel at the speed of light. Now, what this says is, if you are traveling below the speed of light, you cannot finish up traveling at the speed of light. If you're below the speed of light, you're stuck. If you're below the speed limit, you're always below the speed limit. But once you recognize that, then that problem that we had, if force is equal to mass times acceleration, can't we go faster than the speed of light? And the answer is no. You have to modify Newton's second law of motion in such a way that you can then ensure that you can not exceed the speed limit. So Einstein realizes he has to modify Newton's second law of motion. Maxwell, he doesn't have to do anything because Maxwell's already obeys special relativity. You only have to do something about Newton. And now you see that c is universal, and therefore, what is the velocity of light? It's the velocity of light in all frames. But velocity is distance over time. So how can the velocity be the same? The distance has to change and the time has to change. So length contraction and time dilation are required if the velocity is to be invariant. I'll explain how that works in the next lecture. So that's the first thing that Einstein has done, is he's modified Newton's laws of motion. But no, not yet gravity. What he does next is, out of this innocuous eta mu nu, which is a number, he pulls gravity out of it. And I've been in this field for many years, and I still can't believe he did that. And we'll see how that works next time out.
Okay, thank you very much. Given the time, I suggest that we actually postpone the set of questions now.